Good morning, or good afternoon, or good middle of the night, whenever you're watching this. This is going to be the lecture where I lay the foundation um, of human joint motions that's eventually coming. But again, as I prefaced in the first video, before you run, you got to learn to walk, and before you walk, you got to learn to crawl, that kind of stuff. Um, so today is where I get into, sorry, something popped up on my computer screen. I wish I had the force, so I could just like slide it. So before we get into motions, we really have to set the stage. I used that analogy last class. Set the stage of the the bulk, the continuum that we move in. What are the rules that we can move about? That kind of stuff, right? So I'm going to start off by, I know this is high tech, right? But the topic of today is movement. That's we're going to funnel it down, and I have some key terms, okay, that I want to kind of define and go over before we get into the lecture. Linear work, straight line work. So that is, I like to look at it as a distance with your resistance. So if you have like a 20-pound dumbbell, that's kind of your resistance, right? That's what you're working against. And if you lift it up 3 feet, you did less work than if someone lifted it up 7 feet, right? Distance with your resistance. So that's work. And as we know, work is, doing something. If I'm trying to lift up something and I don't make it move, then I haven't done any work, even though I was given effort, I was given energy. But work is what have you done for me lately? You got to actually make something move for it to count as straight line work. And so that's going to be important when we get into understanding motion, because sometimes we have motion where there is no distance with my resistance. So, in other words, when I move my arm up, the resistance that I feel because of gravity pulling down my arm, I literally make it go up. I have distance with my resistance. But sometimes I can move my shoulder. Let me get right here and show you. Sometimes I can move my shoulder in a different way. There's motion, but my resistance isn't going anywhere. There's no movement of it, right? So it's different. It's a different type of motion. And I'm going to explain what the differences are, but I'm just showing you that movement, there are differences, that are nuances with motion. Okay, so you're going to hear me refer to linear work, and that's just distance with your resistance. Movement in straight lines up. That's what linear means, right? Straight lines. So you're moving something up or down or forward or back or left or right. There's some translatory shifting of movement of stuff there, okay? Another term I have is center of mass. You guys may have heard of this as called center of gravity. The same thing, okay? It means the exact same thing. In biomechanics, though, we refer to it as center of mass because it's irrelevant of gravity. It's just basically the average distribution of the stuff that any object has. So the center of mass of this baseball, I'm going to refer to this a few times today, is where the mass of the ball is distributed evenly left and right, up and down, and then front and back. So if this ball has equal stuff on all three sides, the center of mass will be inside the ball, right? Somewhere in the middle. The center of mass of Hugh is the point at which all of your mass is evenly distributed up and down, left and right, and front and back. It's somewhere, you know, around your belly button, inside of you, right? Because you distribute it front back. The reason center of mass is important is because when I talk about distance with your resistance and linear work, I'm going to usually refer to the center of mass of things. And the center of mass doesn't have to just be you. It could be anything. It could be the center of mass of my forearm. Let's see, something just popped up on my computer. Sorry about that. The center of mass of my forearm, I could define, hey, where's the center of stuff with just this segment? Well, where's the stuff evenly distributed? Somewhere around here. What about the center of mass of my arm, right? Maybe there's more stuff here than there, so maybe the center of mass is over here. So I'm going to refer to center of mass, and I'm going to define which segment we're talking about. So that way, when I say, hey, look how you have linear work of your arm when you throw a punch, meaning that the center of stuff of just that arm shifts. It goes forward, it comes back, it goes up, it goes down. Okay? Distance to your resistance, linear work. Center of mass, the average distribution of stuff in any segment that we're talking about. A couple other concepts I want to introduce to you guys for today's lecture. The difference between pure rotation and pure translation. Now, pure, think of it as a continuum, meaning that you have pure rotation and pure translation. And funny enough, that goes back to center of mass, kind of. So pure rotation is when you have one point about a center of mass. I'm going to use, let's say this little dot formed by the magic ink pen is the center of stuff of this manila folder, which it's not, because you have more stuff on the right side, because you see how you have that little lip? That's more stuff. How do I know? Watch, if I let it go, it's going to rotate towards the heavier side. But just pretend, okay? Pretend it has equal stuff. Pure rotation is when all of the points about an object rotate about a fixed point, usually the center of mass. And is there motion? Yes. But is there linear work? No. What I mean by that is the side that my hand is on, it's going down. And you're like, well, Dr. Campbell, that's linear work. But at the same time that this part goes down, the other side goes up. And so it cancels out. So as one side goes down, the other side goes up. As one side goes to the right, the other side goes to the left. And that means that the center of stuff stays balanced. It stays in one point. You think about how a professional basketball player might spin a basketball on their finger, right? The ball is moving. But is it translating? No, it's pure rotation. In other words, there's motion of all the different parts, but it's perfectly synced around the center of mass. The center of mass doesn't go anywhere. Okay? Pure rotation. When all of the parts are moving, but the center of mass stays still. A couple other examples of pure rotation is a merry-go-round. That's a good example of pure rotation. So let's take our little folder and do like this. And imagine kids on a merry-go-round, right? Well, let's imagine there's no kids on the merry-go-round, just the merry-go-round. And it's spinning around. And we know that we don't have to worry about the merry-go-round like rolling away. It's going to stay in the same place. When you were kids playing on the merry-go-round, you knew when you came back the next day it was going to be in the same place. Why? Because the stuff stayed still. Even though it was rotating, moving, the center of mass didn't go anywhere. It doesn't go up, down, left, right, front, back. Okay? Another example of pure rotation is, imagine getting a car, the oil changed on a car, and the car is lifted up and the mechanic spins the tires. So the tire has a center of mass. There's just as much tire up, down, left, right, front, back. There's the axis of rotation, which is about the center of mass in this case. And so the mechanic can spin the tire with pure rotation, and the center of mass isn't going anywhere. There's no linearity, there's no straight line motion associated with it. So that's pure rotation. Pure translation is nothing but straight line motion. There is no bit of rotation at all. So pure translation would be if this baseball, all of the stuff stayed in the same exact place, nothing to do with rotation, and just the baseball went up, down, left, right, forward, back. Pure straight line motion, pure translation, no rotation at all. Every point stays the exact same point, 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 shift, point, 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 point. So imagine if we had these 3 points and there was rotation involved. Well, now this point didn't translate, right? In other words, when I went rotation-wise, this is further away and this is closer to the original 3 points because there was some rotation as well as the translation. So pure translation is when it's nothing but straight line motion of a segment. Now those are 2 extremes, the 2 main extremes of motion. So we have to remember a simple question like, did it move? Which is a question we're going to ask a lot in analyzing human motion. Did it move? Can have 2 different meanings. Did it move in our straight line stage? Did it move up, down, left, right, front, back? Or did it move angularly? Did it move rotationally? Did it move through spin? Did it move through shift or did it move through spin? Okay, 2 different things. Our joints, we rotate in order to translate. So that statement, we spin in order to shift, should tell you that a majority of human movement is a combination of those 2 concepts. Some people like chocolate ice cream. Some people like vanilla. And some people like swirl. A combination. And swirl is a different word, but we know it's a combination of chocolate and vanilla combined. So even though swirl is its own word, we know that it is, what is chocolate, what is vanilla. So we have a term for swirl in anatomical kinesiology. We have the straight line motion, we have the rotational motion, and when we put those 2 things together for a combination of straight line and rotational, we call that general motion. General motion. General motion is how we move a lot. Rarely is our motion purely rotational. And it's impossible for us to move ourselves with pure translation. Let me explain what that is in a very silly example. Pure translation would be if this segment of my hand shot out of my forearm, like like Baymax from Big Hero 6, where he has like the hand that shoots a rocket. That's pure translation. Pure translation is pure dislocation. Like if you just take one bone and translate it from the other, that's a bad day. That's a bad day. But if we translate with rotation, we can shift the center of mass of things. We can make segments go forward and come back. We can make segments go up and come down because we have the combination of translation going up, because we have the ability to rotate things. And when we rotate things at the same time, like when I do this, I have simultaneous rotation of my shoulder and my elbow. Notice my elbow is about at 90 degrees right here. When I bring my arm up, my elbow is no longer at 90 degrees. Why? Because I rotated it. So by rotating my shoulder at the same time as rotating my elbow, I get translation. And translation for us humans is useful. Why? Because we can do work. We can do linear work. We can move things. We can move furniture. We can move ourselves. We can jump up in the air and make our mass go up and down and squat and press. But in order for us to translate our hands, we have to rotate our joints. The hand is not a joint. The hand is just a representative. It's a representative of what our shoulders and our elbows, our feet are not joints. Our feet are just representatives of what our knees and our hips and our pelvis is doing. Okay? So that's important to understand. These terms are good to review. All right? Movement. What does it mean to move? I have nothing but the best props here. I made another little diagram for you. Pause it if you need. And this is showing you how linear straight line motion, 3 dimensions, because I can go up, down, left, right, front, back, length times width times height. We measure it. We discuss it with the concept called an axis. Right? So in mechanics, remember we have this kind of stuff. 2 of these are easy for me to show you. One of them we got to kind of have to use our imagination, but that's okay. The x-axis, it's like a road. But on any road, I mentioned this on Monday, I can go in 2 different directions on each road. I-10, I could go east or west, right? So the x-axis, I can either travel in the positive x or the negative x. So think about me doing work, linear work. Maybe I'm shifting furniture. I can shift the furniture this way, or I could shift the furniture that way. But in both instances, I'm in the x dimension. I also have a y dimension, an up-down. And I can go up or I could come down. I could go in the positive y, I could go in the negative y. So think about an elevator, shifting you, doing linear work on you, making you go up, letting you go down. We do that. We doing squats, let ourselves go down, make ourselves go up. But again, the trick is we translate our mass because we are rotating our joints. Now, the third dimension in straight lines is a little tricky. I'm going to show it to you in a couple of ways. Notice how I put positive z bigger than the negative z because I wanted you to see depth. I'm trying to show you that positive z comes out at you. Boink, boink. You don't have to pay extra for sound effects. Positive z is coming out at you. Negative z is coming back out towards me. So if you were moving furniture like this, moving it in the positive z, moving it in the negative z, but it's still the z. I guess we could talk about furniture in the y too. If you had to pick up the furniture with a friend, right? 1, 2, 3, lift. You pick it up in the positive y. You'd move it across, maybe in the positive z, and you'd set it down in the negative y. Okay? So the point is, in linear world, our 3 dimensions are discussed in axes, like a Cartesian plane, where we have the x, the y, and the z. On Sesame Street, we'd say the up, the down, the left, the right, the front, the back. Right? Layman's terms. I'm all about layman's terms. But it all means the same thing. Now, where things can get confusing is you say, well, man, Dr. Campbell, that sounds too simple. I can move that furniture infinitely many ways. I don't have to move it in a Z or an X or, okay? Well, any way you move it is in a combination of these 3 planes. Simply put, remember north, south, east, west, right? Well, what if I'm traveling here? Well, you're going northeast or northwest or southeast or southwest. So it's the same thing with our 3 main straight line dimensions. Anywhere you move, that furniture has got to be in a combination of these. There's no rule that say you have to move it purely in the positive x. But if you go here and up, some of that motion is in the positive x, some of that motion is in the positive y. If you take it there and across, some of that motion is in the positive x, some of that motion is in the positive z. Okay? Everything has to be a combination of these in straight line world. Okay? Now, in rotational world, this is where things can get a little confusing, but they shouldn't. All motion, I don't want to say all, but a lot of motion in terms of discussion always refers to linear because it's the easiest. It's the easiest to understand. This way is the opposite of that way. That's simple. And we have simple analogies like north and south and east and west. Rotational world is not as easy to talk about because in rotational world, you don't have to go anywhere. You have to spin somewhere, but you don't have to go anywhere. Merry-go-round, right? So what I did is I drew an example of 2 different ways something can spin. Here we had 2 different ways something can shift. Here is 2 different ways something can spin. Something can spin counterclockwise and clockwise. Little hamster should be like, whoa. You've heard it, but I don't think you've ever maybe had it applied to how similar it is to straight line world. Anything can rotate 2 different ways. Now, what I want you to notice is, notice the similarity. Hey, the X, I can go this way, and then if I turn around, I can come back and be where I started. I can travel in the negative X, come back, travel in the positive X, and be where I started. Check this out. I can rotate in the counterclockwise, stop, turn around, and then rotate back into clockwise and be where I started. So what I'm trying to get you to see is that even though this is two different directions of spin, it's in the same dimension of spin. Because objects also can spin in dimensions. We have 3 dimensions of straight line motion, X, Y, Z. Guess what? We have 3 dimensions of rotational motion. But we don't refer to them as X, Y, Z. We refer to them as planes, sagittal, frontal, transverse. That's what that means. Dimensions of spin. So check this out. This rotation that I'm showing you right now, because it's the easiest to see, this is tough to see. This is even tougher to see. So I'm showing you this one. Think about the straight line. Where does the straight line come from? Look how this rotation would occur about a fixed point, an axis. Which axis is this? This is the one that comes out at you and comes in at me, the z-axis. So we have a rotational dimension that occurs about a straight line, a fixed point. Guys, that's where the rubber meets the road. The rubber meets the road with axes. Axes are beautiful because not only can they serve as straight line dimensions of movement, but they also serve as the straight line fixed point about which our rotational dimensions occur about. To put that in perspective, imagine a gymnast who wants to rotate on a high bar. You know what a high bar is? A high bar is where you get on the bar and then you rotate, you rock and you rotate. If the high bar was like this, the gymnast can't spin like this, and the gymnast can't spin like this. The bar won't let him spin. The only way the gymnast could spin is like this about the high bar. And if I rotate the high bar, the only way the gymnast could spin is like this. The gymnast can't spin like this about the high bar, or like this. The gymnast must spin, it's a special word, it's a secret word, perpendicular. The gymnast must spin perpendicular. If this is my axis, I have to rotate perpendicular. If I change the axis, I change the dimension of spin. Watch one more. This is a gymnast. This is a gymnast. This is an exotic dancer. Okay? Just seeing if you're awake. So, notice, perpendicular. As I change the axis, so doth I change the spin. That's cool. So, going back to our clockwise and counterclockwise, this is one dimension. How do I know? Because it's about the z-axis. Z-axis is a straight line dimension. Therefore, I'm going to have a rotational dimension perpendicular to it. That's one. What about the x-axis? Well, the x-axis is a straight line dimension. I have to have rotation perpendicular about it. It's a rotational dimension. Got the z, got the x. What am I missing? The y. No problem. This is rotation about the y-axis. So 3 dimensions of straight line, X, Y, Z. 3 rotational dimensions. The rotational dimensions occur about the X, about the Y, and about the Z. Got it? Now, so what? We got to give them names, just like we gave the X, the Y, and the Z names. That's typically mechanical terms, X, Y, Z, clockwise, counterclockwise. That's all mechanical terms. We are biomechanics. In anatomical kinesiology, we got to bring it back to terms that we use to apply the physics to the human body. So, it's all in your notes. The word we give for the X, the straight line that will serve as an axis about which motion is going to occur. Rotational motion is going to occur. We call that a bilateral axis. So we're just taking the term X and we're replacing it with bilateral. Why bilateral? Well, because in our body, if we have an X-axis going through one side, it's got to come out the other side to side, in one ear, out the other. Remember that phrase? In one ear, out the other, side to side, in one side, out the other side. My right side to my left side, my left side to my right side. It's a side-to-side axis that allows rotation perpendicular to it. Now, if the axis is called the bilateral axis, what is the rotational dimension called that is rotating about it? What do you think? Sagittal plane rotation occurs about a bilateral axis. So we have a name for the rotational dimension that objects can spin in. The first dimension that I'm teaching you is sagittal plane rotations that occur perpendicular to a bilateral axis. So if you nod your head, so I'm saying, hey guys, do you understand? And you're like, that is a sagittal plane rotation about a bilateral axis. What are some other sagittal plane rotations? Doing shoulder raises, there's your bilateral axis, there's your sagittal plane rotation. Doing elbow curls, there's your bilateral axis, there's your sagittal plane rotation. Spirit sprinkles, bilateral axis, sagittal plane rotations. Bilateral axis, sagittal plane rotation. Baby steps, guys. Think of it like this. Before we move on to the other two, we got one down, we got two to go. Think of it like this. If you were coaching a child, working with youth, and you wanted to give them simple tasks to move in a straight line, okay? Or if you were a coach doing a football drill with the football, and you'd say, come to me, and they come to you, and they go back, and they go back. Left side, and they go left. Right side, shifting. Down, and they do like a burpee. Those are simple commands to express straight line movement variations. Down, they go down, they come up. Left, they shuffle left. Right, they shuffle right. To me, right? Front, back, left, right, up, down. There's an easy practical rotational equivalent to that. Think about how many ways a child can spin. A child can do a front roll or a back roll. Like if you said to a child, hey, show Papa how you do a front roll. the child would spin in their sagittal plane. So imagine a child doing a front roll. That rotation would be in the sagittal plane about their bilateral axis. In this case, it would be their center of mass if they're rolling their whole body. But a bilateral axis, because that fixed point goes through one side and out the other side. And it doesn't matter if it's left to right, right to left. It's an imaginary fixed point. It's side to side. So that's the first way a child can demonstrate a roll or a full body spin. But there's more. Oh, good job, Junior. Hey, show Pawpaw how you could do a cartwheel. Do a cartwheel. And so going back to the roll, you could roll forward or you could roll back. Two different directions of rotation in the same dimension. Same thing for a cartwheel. Cartwheel to your right, cartwheel to your left. Now, the fixed point for that cartwheel is now here. If you're doing a cartwheel, now the rotation is occurring about a z-axis. And the word we use in biomechanics for the z-axis is the anterior-posterior axis. Why? Because unlike the bilateral that's coming in the sides, in one side out the other side, the anterior-posterior axis is coming from the front and out the back, anterior to posterior. Real simple, real descriptive. So a cartwheel would be rotation, kind of like how we did here, right? If I did a, watch, I'm going to draw a whee, right? Do a cartwheel, it's going to be about whee, go back the other way, whee, woo, wow. That is a frontal plane rotation about an anterior-posterior axis. So the first one, we had a bilateral axis, sagittal plane spin. This one, we have an anterior-posterior axis and what we call a frontal plane spin. A cartwheel, that's the analogy I want you to hold on to right now. Cartwheels would be the frontal plane whole body rotation. But of course, we could rotate in the frontal plane and it doesn't have to be our whole body. Frontal plane, frontal plane, frontal plane, frontal plane. All about the anterior posterior. Put it in my tummy, frontal plane. Put it on my wrist, anterior posterior, frontal plane. My knuckles, frontal plane. Okay? Frontal plane rotations. It's a dimension. It's a rotational dimension. Now, let's think about the last way a child can spin. Front roll, back roll. Cartwheel to the right, cartwheel to the left. Oh yeah, when I was a kid, I used to do this all the time until I got real dizzy. Spin to your right, spin to your left. The merry-go-round. You spin like a top. Kids just rotating, twisting, spinning around. That occurs about a y-axis. Think about it. It's a y-axis, but we don't call it a y-axis in biomechanics. We call it a polar axis. Some people might refer to it as a longitudinal axis. Guys, it's the same thing. Cat, minu, it's the same concept. But we need to call it the same thing for this class to make sure we're all on the same page. So we're going to say a polar axis, like poles, right? The Earth spins about the poles. So a polar axis allows rotation in what we call a transverse plane. Transverse plane rotations occur about a polar axis. That's our third dimension of spin. So if I'm saying, do you understand? And you go, that answer is given in the transverse plane about the polar axis. Okay? And there's other rotations that occur about the polar axis. My radial ulna joint rotates about a polar axis. Okay? So, to summarize, First of all, don't freak out because we are going to practice. I'm going to give you analogies. I'm going to give you perspectives. There's a lot more to this, okay, before we can get into joint motions. But I need to introduce you to these concepts, and I need you to also understand that the planes and the axes are married. That swirl, the planes and the axes are the basis of general motion. The axes are the straight lines that serve as the scaffolding for rotational stuff. So if you really want to look at it, putting everything together, if you have a joint that has an axis that allows rotation, the general motion is going to be, as there's rotation, there can also be straight line movement of that axis, of that joint, the center of mass of the segment. And that's general motion. Okay? So, in summary, axes are our straight line dimensions, and planes are our rotational dimensions. Our axes, we have bilateral, anterior, posterior, polar. Rotations that occur about the bilateral are sagittal plane rotations. What occurs about the polar? Transverse plane rotations. And what occurs about the AP? Frontal plane rotations. Okay? As always, if you guys have any questions, please email me, text me. I'll do review videos as people come in with questions. I could do review videos that I could post up for you guys. To me, the best way is to practice these concepts is around the house, at the bourgeois, at the gym. Anything, you're going to start to notice things you never noticed before, like this bottle of water. When I rotate the cap, that's pure rotation until I lift the cap up, right? Well, you could be like, technically, as you rotate it, it moves up. Well, you're right. But if I want to look at the plane, what plane is this cap rotating in? And when I say in, that's the dimension that it's swimming in, that it's moving in. Transverse plane. Okay, it's rotating in the transverse plane. Great. That must mean it's rotating about something. That's what an axis is. It must be rotating about a mythical straight line that represents an axis. In this case, polar. Now, could I make this cap and bottle rotate in other dimensions? Absolutely. What about like this? It's rotating in the sagittal, about the bilateral. What about this? It's rotating in the frontal, about the apial. Get it? Same bottle, same cap. Transverse, sagittal, frontal. Spin. Transverse spin. Hey kid, spin to your right, spin to your left. Hey kid, do a front roll or a back roll. Hey kid, do a cartwheel to your right, do a cartwheel to your left. Okay. You're going to notice opening cabinets. What dimension? What plane? Opening things, moving your feet, moving your arms, moving your body. You could practice these concepts. All right? On Friday's lecture, we're going to get into some of the gray. Like, wait, I'm at my house. I don't know if this is sagittal or this is. And that's where I'm going to teach you about references. We have to have references. We have to set the parameters of what it is to be in the front, to the back, to the side, to the side, to the up, to the down. Ups and downs kind of take care of themselves, right? But side to side of a classroom, in other words, this could be the front of this classroom, but the front of 153B might be there. So all it is just about setting these perspectives, setting your scaffolding for your framework of 3D motion, and then playing in it, playing on your stage, and applying your concepts to your stage, okay? All right, guys. Y'all have a good day. Hit me up if you have any questions. Later.